Hello and welcome to another lecture session of classical motion of a single particle. So, in this session I will rather discuss a very small but very nice concept of beats. So, if you remember, in the case of a forced oscillator you have the equation of dynamics to be like this. Where this is the natural frequency, this is the displacement vector, and this is the double dot means this is the acceleration, this is the displacement, and this is the forcing term, of course m being the mass of the oscillator, okay. And this makes the equation to be second order linear non-homogeneous ordinary differential equation, okay. And since we have non-homogeneous, because the right hand side is non-zero with a function of time, okay, we should find both the complementary functions. So, x will be consisting of the complementary function and the particular integral, okay. So, complementary function is the solution of this equation when this right hand side is assumed to be 0, and particular integral is the solution of this equation with this right hand term being present, okay. So, if you remember that in order to discuss the solutions of this type of equation, what we have done, we have cast the equation in a complex form, where we said that this is the complex equation and we have some f to the power gamma t by m, where f is the complex amplitude which can take care of the initial phase of the forcing as well. So, here we are of course considering a special case of periodic forcing with frequency gamma, okay. Now, we assume gamma is not equal to omega. So, this is not a resonance case, not a resonance. However, we can say gamma is almost equal to omega, and let us say gamma is equal to actually omega plus epsilon, okay. Epsilon can be positive or negative both, that is not a very important thing here, but epsilon is non-zero here, but it is very small, okay. So, I can actually write epsilon is very small with respect to omega, okay. But somehow this is just a quantity which says that gamma is not equal to exactly omega, but it is quite close to omega, omega or omega 0 to be very precise. Yeah, I am sorry, many a times I just mix between omega and omega 0. So, please bear with that a little bit. So, omega 0, yeah. Then we know the equation, the solution for the equation will be simply z, which will now be the complementary function. So, y complementary function plus y particular integral, and the complementary function will be given by a e to the power I omega 0 t, okay, plus b e to the power I gamma t, okay. A and b both are complex amplitudes, and that is why they are taking care of the initial phases, okay. If I have this relation gamma is equal to omega 0 plus epsilon, if I can write this one as a e to the power I omega 0 t, and this one I can also write then b e to the power I, gamma is omega 0 plus epsilon. So, I can write omega 0 plus epsilon t, okay, and I can write e plus b e to the power I epsilon t times e to the power I omega 0 t, okay. Now, you see this is a function where this is a periodic function, this is also a periodic function. Okay. Now, this has a frequency which is omega 0, this has a frequency of epsilon. You remember that A being a constant quantity, okay, it does not change the periodic nature of the whole function. Okay. Maybe the initial values and the final values will change, but not the periodic nature. Okay. So, since epsilon is very, very small with respect to omega 0, this part will have a frequency which is much smaller than this part. In this way, we can think of a case where we have a product of two periodic functions, this one, and one has a greater frequency than the other. Then in general what happens, you can see in nature, whenever you have an instance like that, then the function with the greater frequency is enveloped by the function with the lower frequency. So, let us say if you have a function, let us say with a lower frequency which like varies like this, okay, like this for example, and then you have a function which varies like this, okay, then actually you can see that this function with the lower frequency is enveloping the function with the higher frequency. Here also we will have something like this. Okay. Now, how to actually calculate the frequency, okay, that we will see here, and how to actually find their amplitudes. So, Z is given by this, and we can actually say that we can think this one as also a periodic oscillatory type of solution with the same oscillatory frequency omega 0, which is the natural frequency of the oscillator, but with a time dependent amplitude which changes very slowly with respect to time. Okay. So, what can we do with this term? So, the amplitude is A plus B e to the I epsilon t. Now, A is a complex amplitude, I can write that is equal to some A e to the power I alpha. So, A and alpha they are now real. B is equal to B e to the power I beta, again B and beta they are real. Okay. So, if you now want to understand what is the A modulus, sorry, AT modulus, so I can call that as A total, which is A plus B e to the power I epsilon t, okay, will be simply this one, A plus B e to the power I epsilon t, and which actually you can write like this, A e to the power I alpha plus B e to the power I epsilon t plus beta. So, the mod of this two terms. Okay. I can write this, I mean in a very detailed manner, so that you can understand what is this. So, this is A cos alpha plus I A sin alpha plus B cos epsilon t plus beta plus I B sin epsilon t plus beta. Okay. So, finally, you will have something very interesting, that is that what will be then the modulus of this. So, if you do this, you will see, you will do properly the modulus calculation, that will be simply. So, from these two terms you will have A square, from these two terms you will have B square, okay, and then for the cross terms you will have 2AB cos epsilon t plus beta minus alpha. Okay. If you are still not understanding how this is, then the best thing is to write this thing in this way. So, I can just write this one in green. So, I am just once again writing this. So, modulus of this thing will be then A cos alpha plus B cos epsilon t plus beta, and then plus I A sin alpha plus B sin epsilon t plus beta, the modulus of this. Okay. And the modulus of this will actually be, now you can do your, so it is like x a plus I b type of thing. So, it will be A cos alpha plus B cos epsilon t plus beta whole square plus A sin alpha plus B sin epsilon t plus beta whole square, okay, and then you will have, yes. So, this is what it is. Then if you do the calculation, you will have A square plus B square plus 2AB cos epsilon t plus beta minus alpha. Okay. This you can easily see. So, now if you have this, then what is the maximum and minimum value of this amplitude? So, of course, one can easily understand that mod AT will then be running between A minus B modulus and A plus B modulus, because you see that when this cos value is maximum, that is plus 1, then this whole thing will be A plus B, because this will be root over A plus B whole square, and you will have A plus B mod. Okay. You just take the positive value. Here when this one will have minus 1 value, this cos, okay, then you will have A minus B whole square root over, and then you take the mod of A minus B. Okay. So, finally, you will see that you are encountering a situation where your amplitude is actually ranging between A minus B and A plus B, and then it is also changing as a function of time in a periodic manner, and the phase part, I mean effectively going with the same frequency as that of the natural frequency. Okay. So, this is a simplified description of a situation which we call beats, okay, where you can see that the phase part is not changing in its frequency, but however, the amplitude part, okay, is actually varying with time, and you will find a variation in the amplitude. Okay. And of course, you have to understand that in beats, finally the amplitudes are bounded between two specific values given by mod A minus B and mod A plus B. Okay. Thank you very much.